Alright, you can see these proofs are kind of long, so I've split the video into two pieces. We're now ready to do the inductive step for problem number 1. Remember what we're doing is we're examining this problem and we're seeing that every one of these is odd when you add 2 times the term before it plus the term that's 2 before that. So in our inductive step, what we need to show is for all the k's that are integers, if k is bigger than 2. Now why bigger than 2? Because we had 2 items in or 2 terms in our sequence which were seeds or initial conditions, a sub 1 and a sub 2. So the subscripts went up to 2. What we need to do here is we have to say if p of I is true for all of the ones starting at the beginning, going up through k, then the one after that, p of k plus 1 is also true. Alright, so what are we going to have to do here? We're going to have to let k greater than 2, k being an integer, and we are going to assume that this a sub I is going to be something that is odd for all of the ones starting at 1 going up through k. And what we need to show, and it is important for you to write what you're assuming and what you're going to show here, we need to show that the next one, a sub k plus 1, is also odd. Okay. Well, we can do this by using our formula that we have been given for how to figure out a sub k plus 1. Well, a sub k plus 1, using this original formula, the original formula that's up here, that a sub k plus 1 is going to be, let me write it out the long way, a sub k plus 1 minus 2 plus 2 times a sub k plus 1 minus 1. I put the k plus 1 in wherever I saw the k in the original formula. So in other words, we need to see that a sub k plus 1, which is equal to, well, if I do k plus 1 minus 2 as the subscript, you see that what this is it's k minus 1, and this is 2 times, well, if I do k plus 1 minus 1, 2 times a sub k. Alright? And the reason we know this is by the definition of our sequence. The definition of our sequence is what tells us that that's true. It was defined in the problem. Okay. Well, notice that a sub k minus 1 is odd. How do you know it's odd? Because we assumed it would be odd if the I was between the 1 up to and including the k. And since it includes the k, a sub k is also odd. And this is by our assumption, which we can call the inductive hypothesis. It was the hypothesis in this if-then statement. We all need to show at the conclusion that this expression, the entire expression, is odd. Alright. Well, what do you know about 2 times a sub k? Well, this is even because if you take any number and you multiply by 2, it's even by the definition of even. Now here's where it gets to be a little bit of fun. Now, if you take an even number, the sum of an even and an odd integer is what? Well, we did a proof about that before. In fact, it was actually done in your text as exercise 19 in section 4.1, and we did that on one of the sheets. And you can use things that we've proven before, such as the sum of an even and an odd is odd, to help you with doing a proof. So what we get is that a sub k is odd. Now I've run out of a little bit of space here, so I'm just going to keep going though. What we can do with this now is we can say, let's just keep this part. Now that we've proven the second part, we proved 2 things. We proved the basis step, and we proved the inductive step. So we could conclude this saying, so by strong induction, what we know is the original statement, which is a sub n is odd. A sub n is odd for all of them starting at 1. And it's important to put in that note that says it's by strong induction in order to complete the proof. If you look at part 1 and part 2 of this video and follow that as a pattern, it should make it so that you can do proof number 5 on the proofs 2 sheet.